Hello, this is Dr. Armand bringing another lecture involving colligative properties of strong electrolytes. We're going to look at a few more examples involving these properties with strong electrolytes. So sit back, relax, and enjoy the show. So here we want to look at what is the freezing point of water in 8.9% mass solution of lithium chloride. Now, unlike with non-electrolytes, lithium chloride is a strong electrolyte. The equation is LiCl, and we're assuming that it goes to 100% dissociation. So for the freezing point equation, delta TF equals Kf times the molality. Now we include the Van Hoff factor. And again, the Van Hoff factor is the number of particles that are formed in solution per mole of the compound, or per compound. And so for lithium chloride, we have LiCl gives us Li plus Cl minus. So here the Van Hoff factor is 2. So that we know. And we know the KF is given to us. So in order to find the freezing point, we need to know the molality of the solution. But we're given mass percent. So what we need to do is convert mass percent to molality. So with mass percent, we assume 100 grams solution. That means we have mass of solute is 8.9 grams. Moles of solute, we don't know yet. And we need the mass of solvent is 91.9 grams, or 0.0919 kilograms. So now for the moles of solute, we need to find the molar mass of lithium chloride. .94 plus 35.45. We get 42.39 grams per mole. So now we can find the moles of solute, mass divided by molar mass. Get 0.210 moles of solute. So now we know the moles of solute, we know the mass of solvent, we can find the molality. So molality is 0.210 divided by 0.0919. We get 2.29. So now we know the molality, we can find the change in the freezing point. Change of delta TF equals 2.29 times 1.86 times 2. Make sure you include the 2, that's very important. So delta TF is 8.52 degrees C. So now to find the freezing point of solution, it'll be the freezing point of the solvent, the pure solvent, which is water, minus delta TF. So we get the freezing point of solution is negative 8.52. So make sure once you find the change, you subtract it from the freezing point of the pure solvent to get the freezing point of the solution. And make sure you include the Van Hoff factor as well. Here we have another problem. It says calculate the molality and Van Hoff factor for the following aqueous solution. A 1% mass solution of sodium chloride has a freezing point of negative 0.593. And we know that Kf is 1.86 degrees C per molal. So to calculate the molality, we need to convert 1% mass sodium chloride into molality. So again, for mass percent, we assume 100 gram solution. We know the mass of solute is 1.00 grams. The moles of solute, we don't know yet. And the mass of solvent is 99 grams or 0.099 kilograms. For the moles of solute, we need the molar mass of sodium chloride, which would equal 58.5 grams per mole. So mass divided by molar mass gives us moles. We get 0.0171. So now we know the moles of solutes, the mass of solvent. We can find molality. So the molality is 0.0173. So now we know the molality. We can find the Van Hoff factor because remember, delta TF equals KF times M times I. So to solve for I, we need delta TF divided by M times KF. So delta TF is equal to the freezing point of pure solvent minus the freezing point of solution. So that would equal 0 minus a negative 0.593. So delta TF equals 0.593. So now we can find I. Oops, I made a boo-boo. This should be 0.173. So let me change that. And we get 1.84. So what does this I of 1.84 mean? This means it's mostly ions with very few formula units. And the way we know this is because sodium chloride dissociates into two particles. So an I of 1 means it's going to be NaCl. An I of 2 means it's going to be all ions. So an I of 1.84 means it's mostly ions with very few formula units. So here we have a weak acid, a 1.35 molal solution. Weak acid solution has a boiling point of 100.83. Does the solution contain mostly ions, and molecules, or molecules? And it gives us the Kb. So again, a weak acid dissociates into two particles. And so an I of 1 means it's going to be all molecules. An I of 2 means it's going to be all ions. So now if we calculate the Van Hoff factor, if it's close to 1, it's going to be mostly molecules, some ions. If it's close to 2, it's going to be mostly ions, some molecules. Now delta TB equals Kb times M times I. So delta TB equals the boiling point of solution minus the boiling point of pure solvent. So delta TB equals 0.83. So I equals delta TB divided by Kb times molality. So I equals 1.18. So this means that it's mostly molecules with a few ions. And so again, with strong electrolytes, when using them with colligative properties, make sure you account for the Van Hoff factor because that amplifies the colligative property because now you have more particles in solution. So that's all for this lecture. I hope you enjoyed it. This is Dr. Armand signing off.